This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
To compare it with an isentrope, where you know that for an isentrope, P is a function of V and the original entropy, S naught, or for a perfect gas, what will be familiar to you is PV to the gamma is a constant. And the isotherm is similar. PV is PV is RT, and so for a specific temperature, P is a function of V. And so those three curves, the Hugonio, the isentrope, and the isotherm, going through P1 and V1 here, for example, they converge here, and the isentrope is tangential to the Hugonio, and we'll see why. So now we're going to look at, firstly, very weak shock waves. And we're going to look at the change in the entropy through a very weak shock wave. So you saw that what I just wrote down, that you could derive from the equations that H minus H1 divided by P minus P1 was a half of V plus V1. Or you can see that if the change in the enthalpy is extremely small, and V changes very little from V1 and P very little from P1, then that will be, the change in H is be delta H, and V plus V1 over 2 will be some V, and we'll have P minus P1 will be delta P. So we can see immediately from the thermodynamic identity that to first order, for delta P very small, if this is very small and delta H is very small, then it's telling you that since delta H is equal to V delta P, the TdS will be 0. So to first order, if you have a very weak shock wave, it's isentropic. Well, that's indeed why we chose the speed of sound to be constant entropy, one of the reasons. Now let's look more generally, because I'd like to show you how, if you have a shock wave, an arbitrary strength shock wave, not just a weak one, how there is a change in entropy and how that depends on the equation of state of the gas. So in general, let's make a Taylor's expansion of H2 from H1. So H is a function of S and P. So we have the first term here. H2 minus H1 is dH dP at fixed entropy, P2 minus P1. And the next order term is a half d2h dp squared, P2 minus P1 squared. And the next term is 1 upon 3 factorial, which is 3 by 2, which is 6, d3h dp cubed at constant entropy, P2 minus P1 cubed. And then, of course, I have, since H is a function of S and P, I have dH ds at fixed pressure times S2 minus S1, and then I have a higher order term, d2h dp ds, P2 minus P1, S2 minus S1. So that's just a mathematical expansion of a function of S and P to, and you'll see why I've kept this 1/6 cube term here and only an S2 minus S1 here. So now we are going to use the thermodynamic identity, which says that TdS is dH minus V dP. And so we can see that T is dH ds at fixed pressure, and the specific volume, V, is dH dP at fixed entropy, ds. So I can rewrite, so now I can, yes, I can rewrite this equation, H2 minus H1, and P2 minus P1 dH dP at fixed S is the specific volume, so it's V1, P2 minus P1, and this dH ds at fixed P will be at T1, S2 minus S1, plus these additional terms, a half dV dP, P2 minus P1 squared, plus a sixth, plus this term here. Now, the other thing that we know is for a shock that H2 minus H1 is a half. Now, where am I getting this from? This is from the basic relationships that I had way back at the beginning here. So I had H2 minus H1 over P2 minus P1 is a half V1 plus V2. That's the basic relationship that I get for an arbitrary shock wave from the conservation laws. So now, so let's work that out. Let's work out this V1 plus V2. And V2, if I make as a Taylor's expansion for it, V2 will be equal to V1 dV dP at fixed S, P2 minus P1, plus a half D2V dP squared at fixed S, P2 minus P1 squared. And since it's a function of S and P, it'll be dV ds at fixed pressure, S2 minus S1. And so now I'm going to put that into this expression here, and I've got a half, so V2, and I'm going to add V1 to that and take a half of it. And when I do that, I'll have, from the shock wave, H2 minus H1 is V1, so it's V1, so V2 plus V1 by a half is V1 plus V1, it's 2V1 divided by 2 is just V1, P2 minus P1, so that's the first term, plus a half dV dP, and it'll be a P2 minus P1 squared, and then this one will be another half that I had, and I'll have a P2 minus P1, and it'll be now an additional one of these, and I have a quarter. So I have another expression here available to me for H2 minus H1. So if I subtract this equation 4 from my equation 3, which was just a Taylor's expansion, if I subtract them, one of them has the Hugonio in it, the other one is just a Taylor's expansion. Then the left-hand side, the only terms that I've got, if I'm subtracting now 4 from 3, so let's go back here to 3, I'll have a T1 S2 minus S1. This V1 P2 minus P1 will cancel. And I think this a half dV dP, P2 minus P1 squared also cancels. And so what I get when I subtract them is T1 S2 minus S1 plus this D2V dP squared term, and I'm subtracting the 1/4 from the 1/6 in the equation 3. This term cancels, and I'm left with this last term, and we're just going to keep that and say that it's of order delta S times delta P. We don't know what that is at this point we won't. We'll just say we don't know what these two terms will be. So it's just order delta S and delta P. So a sixth minus a quarter, so this is 2/12 minus 3/12. So that'll be minus 1/12. So if I take this to the other side, S2 minus S1 will be 1/12 of d2v dp squared P2 minus P1 cubed to lowest order. So that's a very important result. It says that the change in entropy is third order in the pressure jump. So if I have a very small pressure jump, it's isentropic, as we said. It's third order in the pressure jump. And you can see that order delta S delta P will be the next higher order term, which will be a P2 minus P1 to the fourth. So to lowest, that's the result to lowest order. So now just let's look at this d2v dp squared. For a perfect gas, and the entropy constant, PV to the gamma is a constant, or if I take logarithms of that, it's the logarithm of P plus gamma, the logarithm of V, is equal to some logarithm of a constant. And so if I differentiate that, I'll have dP over P is gamma dV, plus gamma dV upon V will be 0. So now I can work out that dV dP at fixed S is minus V from that dV dP at fixed S is obviously from here minus V over gamma P. And so now I can find the second derivative of that, and it'll be minus dV dP divided by gamma P plus, and I differentiate that with respect to pressure, plus V over gamma P squared. So that's the expression for it, and it's, so I can replace that by this term here, and I get V over gamma squared P squared plus V over gamma P squared, and that gives me, if I make the denominator gamma squared P squared, that'll be a gamma plus 1, I get 1 here, and I have a gamma here, gamma plus 1V over gamma squared P squared. And so if gamma is greater than 1, P squared is a positive quantity, and the specific volume is, of course, a positive quantity. It's 1 upon the density, so that's the mass per unit volume or the volume per unit mass. So that's a positive quantity, so that for this perfect gas, this thing is a positive quantity. And since S2 minus S1 has got to be positive, and this is a positive quantity, then for d2v dP squared greater than 0, like a perfect gas, then P2 minus P1 has to be greater than 0. In other words, the only possible shock is a compressive shock. You go from a lower pressure to a higher pressure through the shock. However, what about the anomalous case where d2v dP squared at constant entropy is less than 0? And there are thermodynamic cases for which that's true. Near the critical point, that could be true. In which case, P2 minus P1 has got to be less than 0 because the entropy has to increase, and that then gives rise to an anomalous behavior of an expansion shock. But so this is what you can get from thermodynamics. You don't have to. You can see shock waves in traffic flow, and that doesn't depend on thermodynamics, of course. So you can derive the same thing. It comes about from the method of characteristics, the breaking of the wave, of an acoustic wave, but you can also derive it here directly from thermodynamics. And for weak waves, we see again that delta S goes to zero, and infinitesimal change in pressure is reversible. The change in delta S is third order in delta P. So that's a very important result. So there it is there. T1 S2 minus S1 is D2V dP squared, which for a perfect gas is 1 upon 12 gamma plus 1 over gamma squared V1 over P1 squared. So now let's just make sure that we understand that. So there's D2V P squared. It's gamma plus 1 V over gamma squared P squared. So that's gamma plus 1 over gamma squared V over P squared, and it's P2 minus P1 all cubed. So that's the change in entropy times T1 for a perfect gas. And if I put P1 is equal to V1 RT1, then if I change this T1 to P1 V1 over R, then I'll have S2 minus S1, and I'll cancel the V, and I'll bring down another P1, and I'll have, just as you would have expected, this is dimensionless. S2 minus S1 over R is dimensionless. And this is now on the right-hand side, P2 minus P1 over P1 all cubed. So now let's just look at the speed of a weak shock. And so let's just think about this for the minute. We proved from conservation of mass that rho 1 U1 was rho 2 U2. And P1 was, P1 minus P2 rather, was rho 1 U1 or rho 2 U2 into U2 minus U1, which could be written as if I pull out a U1 here, then this will be a rho 1 U1 squared, and I'll have a U2 over U1 minus 1. And U2 over U1 is rho 1 over rho 2. So I can write it like this. And if I pull out the rho 1 here in front, I'll have rho 1 squared U1 squared, and I'll have 1 upon rho 2 minus 1 upon rho 1, which is V2 minus V1. So that the change in pressure across the shock is U1 squared over V1 squared V2 minus V1, or U1 squared is equal to, let's multiply this out, V1 squared into P1 minus P2 over V2 minus V1. Or, that's the same thing if I just change this sign from P1 minus P2 to P2 minus P1, because P2's, I'm thinking, is larger than P1 usually. Then this is minus V1 squared, P2 minus P1 over V2 minus V1. So, for weak waves, U1 squared is minus V1 squared dP dV. So if this is a very weak shock wave, P2 is very close to P1, this will be delta P divided by delta V on the Hugonio. So that's the same thing as since the density is 1 upon the specific volume, dP dV is times minus V squared will be simply dP d rho, or dP d rho will be dP dV, and differentiating d rho dV will be minus V squared. All right, so U1 squared is the speed of the flow relative to a stationary and vanishingly weak shock. And so here's our shock, and the U1 is the speed of the flow relative to a stationary, vanishingly weak shock wave. And evidently, dP d rho on the Hugonio is identically equal to dP d rho on the isentrope, since For delta P going to 0, delta S, it goes like delta P cubed, and so that goes to 0. So, and dp d rho on the isentrope is called the speed of sound, A1 squared. So I can deduce, so the propagation of an infinitesimal shock in a stationary fluid is U1, and U1 will be A1 squared. So A1 squared will be U1 squared, which is dp d rho on at constant entropy. Now, let's just go a little bit further and look upstream and downstream of a weak shock wave. So the conventional case that I mentioned is that d2v dp squared is, I worked it out for perfect gas, and it was positive. That's the conventional case. So let's remind ourselves, d2v dp squared will be in the limit as delta p goes to 0, it's dv dp at 2 minus dv dp at 1, p2 minus p1. So the vdp at 2, so the change in volume, so that's the slope of this Hugonio locally, which is an isentrope, that will be a small negative number because for a given change in delta P from here to here, delta V is negative. So that's, so delta V is a small change for a large change in delta P, or relatively larger change. And so that's a small negative number, and this is a large negative number here, larger down here. And so I get that U1 squared is minus V1 squared, P2 minus P1 over V2 minus V1. And since V1 squared is 1 upon rho 1 squared, and rho 1 U1 is rho 2 U2, it also tells me that U2 squared is minus V2 squared, P2 minus P1 over V2 minus V1. Now they're from the shock relations, from the Hugonio, from the shock relations. So let's look now at conditions 1 and conditions 2 so that we can decide why shocks are like they are. So U1 squared from the shock relationship is minus V1 squared delta P divided by delta V, and U2 squared is minus V2 squared delta P over delta V. And delta P is P2 minus P1, and delta V is V2 minus V1, which is negative. Whereas the speed of sound, A1 squared, is dp d rho at fixed entropy at the point 1. And that will be minus V1 squared dp dv at fixed entropy. And I showed you that it's isentropic, so they're tangential for very small changes. But the magnitude of dp dv at 1 is much less than the difference delta p divided by delta v for a finite shock wave, whereas delta p delta v at 2 so this is up here at 2, and as I've said, delta p divided by delta v at 2, the magnitude of that is much greater than delta p over delta v. From that it follows that u1 squared, and which is delta p over delta v, which is u1 squared over v1 squared, u1 squared is much greater than a1 squared, which is 1 upon v1 squared dp dv, or, sorry, minus v1 squared dp dv. So U1 squared is much greater than A1 squared, and U2 squared must be less than A2 squared. So that's the conventional case, which means that M1 squared must be greater than 1, and M2 squared must be less than 1. And that is a terribly important result. So shock waves occur when S2 is greater than S1 only in supersonic flow. That is, I have to have a supersonic flow, i.e. for M1 greater than 1, in which case M2 is less than 1, and P2 is greater than P1. For a stationary flow, the shock will be moving downstream into the stationary flow, and the fluid behind the shock moves to the right. So if you just make the Galilean transformation. Now, in this anomalous case, and I haven't worked it out for you, as it's tedious in a way, d2v dp squared less than 0, you get anomalous effects, and it may occur near the critical point. But again, you can show that U1 is greater than A1, and U2 is less than A2, but P2 is less than P1. So we have an expansion shock from the supersonic flow to the subsonic flow. So that's entirely anomalous. So now let's look at the relations for a normal shock in a general fluid. So the relations for a normal shock in a general fluid. So all I know about this fluid, and it could be steam, for example, all I know about it is that I have a table of H versus S and P. So it's steam, it's not air. Or it's some products of combustion from some solid rocket motor. So H is a function of S and P, from which we could find H as a function of P and rho, because you'll recall that I can get the specific volume and 1 upon the density from dH dP at fixed entropy. So if I am given rho 1, U1, and P1, then I automatically, from this relationship here, I automatically have H1. And so now how can I solve for the shock? Let me choose a rho 2. If I choose a rho 2, and I know rho 1 and U1, it automatically gives me a U2. And from equation 1 and from equations 2 and 3, I get a P2 because I know U2 and I know rho 2. And so I've chosen rho 2, I know rho 2, I know P2, and I know H2. And so from 4, if that's not, if for those values of P and rho I don't get the correct H2, then I have to make a new estimate for rho 2. And I keep iterating to find the solution to these 4 equations. However, we can work it out easily for a perfect gas. So we're going to work it out in general, but what I just described is what you'd have to do if it were steam. You'd have to go to your steam tables and you'd have to work out how to calculate the pressure rise through a normal shock in some supersonic flow of steam. So for a perfect gas, then A1 squared is, well, dP d rho, which is gamma P1 over rho 1, or gamma RT. You know that well. So U1 squared times rho 1, U1 squared divided by A1 squared is the Mach number squared. And So what I've done here is I've said rho 1 u1 squared over p1, well, let's just put that in. Rho 1 over p1 will be gamma over a1 squared. So this will be gamma u1 squared over a1 squared, which is gamma times the Mach number squared m1 squared. And similarly, that u1 squared, I can work that out. And why do I want to do this? Because I want to go back to the relationships that apply for a shock wave. For an arbitrary shock wave, these are the relationships that hold. That's conservation of mass, momentum, and energy. So u1 squared divided by, so what I want to do, if I'm going to divide this equation by h1, I'm going to get h2 over h1, and then I'm going to have 1 over 2h1 u1 squared. And so let's see how I'm going to work that out. So u1 squared over 2h1. So h1, how am I going to work that out? What is h1? Well, h is CPT, and CP is for a perfect gas, constant specific heats. CP is gamma R over gamma minus 1. So CPT is gamma RT over gamma minus 1. So that's A squared. I'm sorry. So that's A squared over gamma minus 1. All right, so now let's work out P2 over P1. So we go back up here. P2 over P1 will be rho 1 u1 squared divided by p1 plus rho 2 u2 squared, but that's also rho 2 u2 squared is rho 2 u2, which is rho 1 u1, and so I can pull that out and I'll have a u2 over u1 in a minute. That's what I'm going to do. So I've done this for you. P2 over P1 will be a half u1 squared over P1, and that will be gamma m1 squared, and then it'll be 1 minus u2 over u1, which is rho 1 over rho 2. And h2 will be 1 plus gamma minus 1, h2 over h1. There's a u1 squared over 2h1, which is gamma minus 1 over 2 m1 squared. So that's what I have for the first term, and the other term is rho 1 squared over rho 2 squared, or u2 squared over u1 squared. So, and now I can work this out in another way, that h2 over h1 will be t2 over t1, which will be p2 over p2 over rho 2, which is t2. So there's an r in here, but the r's are going to cancel for the top and the bottom. And I'm going to divide by t1, which is p1 over rho 1. And that, I'm going to rewrite that as P2 over P1 times rho 1 over rho 2, and I'm going to call rho 1 over rho 2 R, which is equal to U2 over U1. So now, H2 over H1 is this expression here, 1 plus gamma minus 1 over 2 M1 squared into 1 minus rho 1 over rho 2, and so that's going to be an R squared. And that's also equal to P2 over P1, which is 1 plus gamma M1 squared into 1 minus rho 1 over rho 2 is again R. So, and that's got to be multiplied by r. So you can see that I've got a quadratic equation here. If I multiply these terms out, I have a quadratic equation for r, for which I can find the roots. And the roots are, and I haven't, it's a little bit of algebra to do it, and I haven't got all the steps in here. But you can believe that if it's a quadratic equation, it's minus b plus or minus the square root of b squared minus 4ac over 2a. So that's all you have to do, put that in there, and you'll get what r is. And the answer is 1 plus gamma m1 squared plus and minus 1 minus m1 squared over gamma plus 1 m1 squared. That's what you get. And that's the square root is this thing squared. So that's how you get the square root out of it. And so you can see that if I take the plus sign here, I get 2 plus gamma minus 1 m1 squared divided by gamma plus 1 m1 squared. Or if I take the minus sign here, then I have gamma plus 1 m1 squared in the numerator and the denominator, and I get just 1. So r is either this quantity or it's 1. In other words, if it's 1, there's no shock wave there at all. So that's pleasing that you get these two solutions in that way.
Why is that?
Beg your pardon?
Why is it when r equals 1, there is no shock wave?
Oh, when r is equal to 1, it means that rho 2 is exactly equal to rho 1. U2 is exactly equal to U1, so there's nothing there. But in general, that's not true. In general, I get that rho 2 over rho 1 is gamma. I can just divide this equation by 2, and r is rho 1 over rho 2, and so rho 2 over rho 1 is 1 upon r, and so it's gamma plus 1 over 2 divided by 1 plus gamma minus 1 over 2 m1 squared, and m1 squared here. So that's a really interesting result, and we're going to take some limits in a minute for weak waves and for very strong shock waves, arbitrarily strong shock wave. So, and we get also P2 over P1 is 1 plus gamma m1 squared into 1 minus r, and if you put this in for r, then you get this relationship here. And that tells you that if I take the 1 to the other side, P2 minus P1 over P1 is delta P. So that's the pressure jump across the shock divided by the upstream pressure. And that's 2 over gamma plus 1 m1 squared minus 1. And I can also work out immediately T2 over T1, which is P2 over P1 times rho 1 over rho 2. And if I put that in for r, I get this result here. And then I can get the ratio of m2 squared over m1 squared. What is the Mach number of the flow beyond the shock compared with the Mach number upstream of the shock? And I know that they should be, one should be subsonic and one should be supersonic. So I get this expression for the Mach number, yeah. For the Mach number, if I put that in, I get this expression for the downstream Mach number. So let us suppose that m squared is 1 plus epsilon. Then if I put m1 squared equal to 1 plus epsilon into this equation for m2 squared, then I get gamma minus 1 into 1 plus epsilon. And gamma minus 1 into 1 plus epsilon. And that'll change the 2 here. And I get gamma plus 1 plus gamma minus 1 epsilon over gamma plus 1 over 2 gamma, down the bottom here, 2 gamma into epsilon. And I can quickly show that, so I can divide both of these by gamma plus 1 and take this one up to the top for small epsilon. So it'll be 1 minus 2 gamma over gamma plus 1 epsilon. And so to leading order in epsilon, this term and this term, gives you 1 minus epsilon. So if m1 squared is 1 plus epsilon, it's just supersonic, then for small epsilon, m2 is just less than 1. Only just less than 1, which is what you might have expected, so that you have a flow that's supersonic, goes through the shock, and it's now just subsonic on the other side. So m1 squared minus 1 is 1 minus m2 squared. They're both equal to m1 squared minus 1 is epsilon, and 1 minus m2 squared is also epsilon. So that's an important result, that you go through the shock and you go from supersonic flow to just subsonic flow. Similarly, for strong shocks, let's take the limit now where m1 goes to infinity. So P2 over P1 will be I'll be able to ignore this term here, and I'll have 2 gamma over gamma plus 1 m1 squared minus 1, or 2 gamma over gamma plus 1 m1 squared in the limit of a very large shock. And so there it is here for a very strong shock. P2 over P1 is 2 gamma over gamma plus 1 m1 squared. And rho 2 over rho 1, which is R, so let's just look at R again. Rho 2 over rho 1 is rho 1 over rho 2. And we solve for R. And so you can take, if you take the limit of m1 going to infinity, then rho 1 over rho 2 will be gamma minus 1. It'll be gamma minus 1 over gamma plus 1. So the density goes to a finite change through even an arbitrarily strong shock. Even though the pressure has gone up to infinity, for a very strong shock, the density doesn't. Why? Because the temperature goes up through the shock. And so there's a limit for the density ratio. And there's what it is. Rho 2 over rho 1 is gamma plus 1 over gamma minus 1. And for gamma equal to 1.4, for air, for example, that limit is 2.4 over 0.4, so that's 6. Yes?
Is this result for ideal gas only or for general flow?
The rho 2 over rho 1, this is an ideal gas result. Yes. I worked it out up with these different values of results for gamma from a perfect gas. And I got that m2 squared, I also had an expression for that. What happens to m2? So you take m1 going to infinity, m2 is going to go to gamma minus 1 over 2 gamma as m1 goes to infinity. So I know now something about very strong shock. m2 goes to gamma minus 1 over 2 gamma. So m2 squared goes to 1 upon 7. And that's because even though the velocity goes down, the temperature goes up. The velocity also goes up, but the Mach number remains constant. And that Mach number behind the downstream of the shock is 0.378. It's the square root of 7, or the m2 squared is 1 upon 7, so m2, if you take the square root of that, it's square root of 7 over 7, and that is 0.378 for gamma 1.4. And I can also work out the change in entropy, and I think I'd better, oh no, I still got some time. So I can work out the change in the entropy across this shock, and I write down again, this is why you see me so often use the thermodynamic identity. TdS is dH minus dP over rho, and for a perfect gas, P is rho RT, so if I take logarithms and differentiate, I get dP over P is equal to d rho over rho plus dt over T. So if I put that in there, dP over rho, then I can write rho is P over RT, and if I'm dividing by the T, I'm going to have, this is going to be H is CPT, so this is Cp dt over T minus R dP over P for the change in entropy. Or, and since if I write dP over P as d rho over rho plus dt over T, so this is Cp minus R dt over T, which will be Cv, Cp minus Cv is, Cp minus R is Cv, or Cp minus Cv is R, and I've written it there, and Cp over Cv is gamma. So this is also an important result, that if I now divide by Cv in here, I'll have ds over Cv is dP over P minus gamma d rho over rho. So S2 minus S1 over Cv will be the logarithm, because I can integrate from 1 to 2. This is a variable of state. So it's the logarithm of P2 over P1 minus gamma logarithm of rho 2 over rho 1, which is the same thing as the logarithm of P2 over P1 times rho 1 over rho 2 to the gamma. And I've worked out for you what P2 over P1 is as a function of gamma for this perfect gas. And this is R, and so this is all a function of Mach number. And a very important result from this is to work out what is the change in total pressure. So in that case, the entropy S2 minus S1 over Cv will be the same as the total entropy at 2 minus the total entropy at 1. S2 is the same as S2T, the total entropy. And I just worked that out. It'll be Cp over Cv, the logarithm of T2T over T1 minus R over Cv, the logarithm of P2T over P1T. And Cv is R over gamma minus 1. So this thing is, the R's cancel, and I get gamma minus 1 here. And of course, T2T is T1T. There's no change in total temperature through the normal shock. So this is 1, or the logarithm of 1, which is 0. And so because T2T is T1T, then the total pressure at 2 divided by the total pressure at 1, the logarithm of that to the minus gamma minus 1 is the logarithm of P2 over P1 rho 1 over rho 2. So I can get, and I've got these expressions, it's just messy algebra. So P2T is P2 over P1 to the 1 over, to the minus 1 over gamma minus 1, and it's rho 1 over rho 2 to the minus gamma over gamma minus 1, and that's another function of M1. And so you can see also that from the first law, TdS, or thermodynamic identity, is the change in HT minus the change in total pressure divided by the density. Well, since the change in total enthalpy is 0, and the change in the entropy has to be greater than 0, it says that this change in total pressure has to be 0, and indeed it is. So these are some of the relations that you can derive. Yes, sorry.
Can you please explain again why the two stagnation temperatures are the same? T.
Ah,
Yeah.
the total temperatures.
The total temperatures.
Yes.
Are they not? Oh, yeah. Okay.
The total temperatures are the same because H1 plus a half U1 squared is equal to H2 plus a half U2 squared. And so HT, which is H1 plus a half U1 squared, it's the total enthalpy when you bring the fluid to rest. So that's HT2 is equal to H1 plus a half U1 squared. Bring the fluid to rest. It's HT1. So they're the same. There's no change in total temperature through the shock. Very important result. And this follows. So now I'm going to tell you about how you use all these shock relations in general. So the first thing is, let's supposing we had a bluff body. Well, we know that if we had supersonic flow, the only way we can bring the fluid to rest on the body at 2 is through a shock. And so the total pressure right here at 2, that total pressure will be less than the total pressure upstream because you have to go through the shock. Because the shock is required because you know that these streamlines diverge, and if the flow were subsonic, the velocity would... If the flow was supersonic, rather, and the streamlines diverge, the area increases, the Mach number would have to go up, not down. So how could I get Mach number 0? The only way to do it is to go through a shock. If I go through a shock, I have supersonic flow here, I have subsonic flow behind it, and now, as I take the area, make the area increase, the flow slows down. So that's a... But the stagnation pressure here at 1, the stagnation pressure, I should say, at 2 is the total pressure at 2, but that's not the same as the total pressure at 1 because there's a change in total pressure through the shock, which we've just seen. So how does a pitot tube work in supersonic flow? Well, let's talk firstly about subsonic flow. How does a pitot tube work in compressible subsonic flow? Well, firstly, in Mach number less than 1, we can bring the fluid to rest at that 2, and so the total pressure right here will be the same. It'll be an isentropic process. We assume that it's an isentropic process, and it'll be the same as the total pressure far upstream, and that'll be the stagnation pressure P0 far upstream. And so this, we've worked that out before. We worked it out from the ratio of the temperatures, and because the pressure goes like the temperature to the gamma over gamma minus 1, then it's 1 plus gamma minus 1 over 2 m squared gamma over gamma minus 1. So that's this the case that we worked out for one-dimensional subsonic flow. So how does it work? Oh, I think I got to quit. Yes, all right, I'll pick it up next time. Yeah, I'll have to pick it up.